To be back. So I graduated 2011. I was a student of Dr. Fang, Dr. Payne, a few others that seem walking today. So I'm really happy to be here. So we recently launched a boutique consulting firm partnering with educators, and Dr. Fang has been involved in this as well. And there was an opportunity that came up with NAEP, which is a national assessment of educational progress in America. So they are the nation's report card. They release assessments that are taken on the computer by children K through 12, and it covers, the core disciplines, math, reading and writing, things of that nature. And so a couple of years ago, they, NCES, which is the organization over NAEP, started exploring what it was like to use automated scoring systems leveraging AI and machine learning technology in order to grade these assessments. So the first assessment was English reading and writing comprehension. And it went over well. It was a challenge that was administered by NAEP. There was a cash prize for the most accurate and some other prizes, for interpretability and things like that. So piggybacking off the success of that, then a year later, they issued this mathematics challenge, where they invited researchers and trade groups to come in and build your best automated scoring engine and for math specifically. And so that's what we did. So Dr. Fang and myself and a couple of my colleagues band together. It was a kind of a tight timeline on it, but we did some really cool stuff here, and so I'd like to show that to you guys. Now, this was compelling to me from a commercial viability standpoint. There is actually a market out there for this, but it's a nascent market. And if you think about it, and I'd like you to kind of keep this in mind as we're walking through some of the slides here, is that like automated assessment scoring, particularly at grades 4, grades 8, national level, it's really a high stakes game. The systems have to be monitored, maintained. They have to be able to score on the same caliber as a human rater would score. And there has to be processes in place to basically ensure that these are not biased and things like that as well. So as you think about that, it's not so much just generating or creating a model or an automation or a program that can do this one time. If there were going to be private interests in developing things like this, it really would, I believe, be an industry in and of itself that would require various level of expertise, from professional educators to data scientists to data engineers. And so that's a very, very interesting angle for me, but then also just to kind of see what was possible as we embarked on this. It was a lot of fun, and we tried a lot of cool things out. And so
pointed to the machine.
Yeah.
There you go.
Just use the mouse and click.
There we go.
The clicker should work.
Okay, there we go. Yeah. So a couple of things. So we did not win the submission, but but when we went into this, there were a few pillars of this, and there really is kind of philosophy around it, because I wanted to make sure that when we started this, we came up with a baseline solution, regardless of how accurate it was, that we could then build on top of and iterate on. And one of the key pillars of my philosophy with this is that it had to be very transparent, and that it had to be very interpretable to anybody that was assessing the machine or anybody that was on the receiving end of the scores. And so the winning submissions in this challenge were black box, neural network type solutions. We purposely chose to stay away from that. And I believe we did come up with a very novel approach here, and have identified areas where if we continue to iterate in certain aspects of this program, that I believe that we could produce results comparable with uninterpretable less transparent versions of this. But to quickly go through this, so there were 10 items to be scored in this math assessment. We developed 10 specific models, so it wasn't one model that serviced all of them. Each one was specific. It was the 2017, 2019 test vintages of this math assessment, and it was the assessments that were administered to grades 4 and 8. So if you think about that, grades 4 and 8, varying levels of English proficiency, grammar is not always great or perfect. And then also, like, they're interacting with computers and typing their results into computers and things like that. And so one of the aspects of this is, that was important as we were developing it is we didn't want to overly influence the actual responses that the students had put into the machine itself. And so, there could have been a route where people go in and potentially, doctor up and do some data cleaning on the actual constructed responses, maybe, look up some word misspellings and correct some word misspellings and things like that. We didn't want to do that at all. We wanted to take the data from the student in its most purest form and see if we couldn't then leverage that information to come to, a reasonable assessment. So simplicity, transparency, they had to be fully automated. So these were 10 things. We set them up as model pipelines. We had data engineering pipelines on the front end that was doing a lot of work, and then some results compilation on the back end. And then some of the key technologies that we used, in the spirit of keeping it simple, we used a bag of words methodology, which is a very rudimentary NLP approach. We'll go into it a little bit here. And then some of the packages, so we used XGBoost. I saw some XGBoost love earlier today. Me personally, it's I'm very familiar with the package. It's very easy to implement. It has withstood the test of time. I always tend to use that as a base model for a lot of things when I'm beginning a project like this. And so it was just the easiest for us to go straight to and implement. And then additionally, we use things like pandas. We use libraries like pandas, scikit-learn, NumPy, Bayesian optimization, and then matplotlib and a few others for some visualization. So the way that the assessment is structured, you'll see here, there were these 10 items, and the score that's being used here is the quadratic weighted kappa score. So this is basically a score that can indicate the similarity of two different things. And so you can have a human-to-human quadratic weighted kappa, which would be close to 1. Now, so if you have a machine-to-human quadratic weighted kappa, you would want that ideally to be close to 1. Generally speaking, like values over 70 or 0.7 or so are generally okay or somewhat similar. But again, if you kind of go back and think about this as being like a high-stakes deal, like you can't have an automated machine that is subpar to human grader and then actually put that into production. So the bar is much higher for a system like this when it comes to quadratic weighted kappa. And then the amount of data that we had to use. So the way that this was set up was they first, them being NAEP, would release all of the data for the training and the validation of everybody's models. And then about a week out from the submission deadline, they would then send out the data that didn't have any of the answers on it, and that was your test set. So then you would basically take your system, score it, send it in, and then you would get the feedback. And a lot of the variables or features that were included in the data sets were things like race, whether they were an ESL student, whether they use things like the equation editor on the computer. There was a constructed response section. And then there was also some sections on some questions where students have the ability to eliminate answers. And so you would see like what answers they eliminated. And so you could, factor that into the modeling as well. Yeah, so like I said, we didn't win and we did okay. We did all right. Some of these were actually quite bad, but some of them were pretty good. You can see that on average, our human to machine quadratic weighted kappa score was about a 0.71, which is okay in some fields, but I think we have to hold ourselves to a higher bar here. We did get up to a 0.87, you know, on a couple questions into the mid 80s. But where our systems did tend to really break down, we also see the human to human system, or the human to human QWK breakdown as well. So, you know, our machine was somewhat consistent with the fluctuation there, the variation there. But obviously a lot of work to do if we were actually going to try to implement this on a wide scale. So you guys can't see this too well, but basically every time I approach a new machine learning project, in my mind it's always, what does the pipeline look like? I try to visualize it in my mind. And for this, there were really three sections, and can be generally applied to any machine learning or AI project. But there's a warehousing, a data ingestion process, there's a feature engineering process, and there's a modeling process. And ours is set up very much similar to that. And so we took the data, it was like flat file CSV type data from the government. We managed to load that up into a Snowflake instance, and then from there is where all the feature engineering really took place. And so I'll kind of like spend some time over the next few slides walking through the feature engineering steps that we took, and briefly touch on the modeling. You know, the modeling really wasn't the tough part. I would say the bulk of the magic in this particular system is in the feature engineering itself. And so as we walk through that, first off, there was just data cleansing. And so as you can imagine, so the test vintages were 2017, 2019. They had different formats that the data was reported back to us, the modelers with. So for example, sometimes in 2017, you would get a logical vector of responses. So this would be like, you know, A, B, C, D would be what the student was looking at. And it was like they selected A, they didn't select B, they didn't select C, they did select D. Other vintages of the test were like 1001s. You'd also have these comma separated arrays like A, B, C, D versus these like semicolon separated arrays on the same thing. So there was an extensive amount of data cleaning that had to go into the front end of this pipeline before we were able to do anything with it at all. And then that kind of leads into how we thought about handling the race and the ESL, you know, concepts. So there was a lot of debate on should we be using race indicators in the models at all? So, you know, Black, Hispanic, white, Asian. How do we use the ESL? Are we introducing bias? A lot of good conversations around that. Ultimately, what we decided to do with this was we took the indicator variable of the student being an ESL student, and we basically created an interaction term with the race and that particular indicator variable. So you didn't really receive the interaction term unless you were an English as a second language student. And then if you were an English as a second language student, then you received the interaction term that was consistent with the race that you fall within. And so I'd like to show you guys a little bit about what the questions look like. So because we built 10 different models and then we got these all sort of served up in the same model pipeline, we were able to really go in and look at each question individually and extract important variables for that question. So in this case right here, you've got this 2666510, 2017 and 2019 vintages. So we did control for the vintage and the model. This is a moderate complexity question, and it is basically which of the following statements must be true about any of the two distinct lines that intersect at exactly one point on the XY plane. And they have to select the right answer, and then they have to submit a constructed response explaining their answer. And then the way that the grading rubric is set up on these is that you have, basically for this one, you have incorrect, partial, or correct. And so if they got the correct submission and their constructed response was adequate, then it was fully correct. Now they could get a correct selection with incorrect constructed response or vice versa, and it would be partially correct, or it would just be flat out incorrect. And so I also have to pause and say, you know, these are like 4th and 8th graders. And so the constructed responses that we received were just like so cute and so funny. I mean, do you guys know Elsa from Frozen? Well, apparently all of these people know Elsa. Because Elsa came up in their constructed responses more than almost any of the digits or numbers like that. Here's another example of one that's fairly straightforward. It's, you know, map the relationship between the input and output. This is one particularly where the answer is 6, so it's 6 times the input is the output. You either get this one correct or you get it incorrect. And so in a particular situation like this, not only did we have the NLP component on the constructed response as a part of the overall grade, but like if you just had 6, if we recognize 6 was in your constructed response at all, then you get that question specific feature in addition to the constructed response feature. On the previous one with the multiple selections, and you know, if I forget which one it is, but if it was like C, you know, obviously the question specific feature for that question is, did you get C, you know, for your answer? And then there were some other ones on the elimination stuff that, like I said earlier, we were able to account for as well. So that's how the questions were constructed. Some of them were quite difficult. Some of them were geometry in nature, you know, using triangles and shapes and stuff as well. And so for the constructed response section, we wanted to keep it simple. So we went with this bag of words approach. And basically, we took the constructed responses. We did, you know, set some parameters in the libraries that we're using so that we like drop stop words, like common words like a and as, things like that. We lowercased everything and standardized the constructed responses from that perspective. But then we basically used some libraries to create what is known as a document term matrix. And it basically takes, a document term matrix takes every single term that is in all of the constructed responses for that entire training set, and that becomes the model's vocabulary. And so what you have across the headers, these column headers, is each column is one of those words, and then each row is the student's constructed response. So in this particular case, about the bird, you know, bird shows up 5 times, about shows up once, heard is 0. And so you can see how you can construct this matrix by pivoting out the vocabulary of the constructed responses across the questions that way. What we ended up doing here is we actually then didn't rely on the output of a model that we put this into. So we took the document term matrix and we ran the multinomial Bayesian library on it, but it was a binomial estimation, binomial classifier on whether or not the student got the constructed response correct or incorrect. So even if they got the question incorrect, but the constructed response was still correct, that was still a 1. Otherwise, it was a 0, just for this feature engineering portion. So what we did then is we took all those 1s and 0s and we modeled those against the document term matrices across all of the different questions. And we came up with the likelihood that a student had a correct constructed response for the question. Now, what we did, though, is instead of using the 1s and the 0s as the output, we extracted the probabilities for that likelihood. And that was what was actually used as the feature for the constructed response piece of the automated system. Because our hypothesis here is that there's degrees of correctness within the constructed response, especially when we take into consideration grammar and English proficiency and things like that. You might have on scale a constructed response likelihood for a particular class or for a particular question that is different than another subset of that group. And so rather than just saying you were right or you were wrong, we went ahead and extracted those likelihoods, used those as a feature to introduce some more continuous representation of whether or not that constructed response was actually correct. And so here's you can't really read this, I suppose, but here's an example for one of the questions, 134067. This was this 6 times input equals the output question. Some of the vocabulary that you'll see in here, you've got words like multiply, but you do have misspellings of words like digit, D-I-J-I-T. And we would expect that from 4th and 8th graders, you know? And so we wanted to go ahead and keep that in there, because if one person is misspelling it like that, at that level, there's a likelihood that there are a lot of other kids that are, and that are spelling it the same way. And so instead of trying to alter that in any way, and change that in any way, and put our influence on the constructive response, we just left it alone. And we let them write. And so you can see here, this is a confusion matrix for this particular Bayesian classifier that we used here. You know, and the results are okay. But again, you know, we didn't use just the zeros, the ones. We actually did extract the probabilities and use that as a feature. And then I also want to touch on some of the interesting aspects of this bag of words approach is that you'll have, so this is a question that was about measuring the interior angles of a pentagon using triangles, basically. And so you would expect to see terms like 180, you know, for triangles, and the term triangle and polygon and things like that. And so, interestingly enough, you do see 180 as a term that is used 175% of the time in correct responses, meaning that it's used multiple times in the same response. So 180 is generally used multiple times in a correct response here. However, 180 is used, you know, well, it's, you know, 8% here, but 540 is used 52%. And 121% can pass and then fail. And so the point I'm trying to drive home here is that simply having a term and using that term as a variable in your document term matrix can somewhat be misleading, because you might actually have the same term in both equally correct and incorrect responses. And so what's interesting is to look then at the ratio, which is the percentage of times that term shows up in correct responses relative to the percentage of times that term shows up in incorrect responses. And I sorted this here, you know, and these are quite small numbers at the top, so they, you know, kind of tend to blow up on the ratio. But you'll start to see things like, you know, 3 times 180, 180 times 3 as being like the top 2 terms that are most associated with this corrected response through this lens. And so you really start to see, you know, the refinement of the terminology that is actually being leveraged within this section of the system here coming to fruition through that lens. So once we got through all the feature engineering, at that point, you know, we're like 60–70% the way through at this point. At this point now, it's mostly just like getting the tables formatted properly, getting everything set up, getting the automation working, and getting it all wired up. So, and we use XGBoost for the model here, but then in order to tune the parameters for XGBoost, we did utilize Bayesian hyperparameter optimization. So this is a very straightforward Python library that's easy to use. Our motivation for using this particular approach was just speed and efficiency. You see, with the Bayesian approach, it uses a surrogate objective function to optimizes that. And as it's running iterations on various parameters to understand, you know, where the optimal parameter for that particular model actually is. And it's just a much faster process than some of the other processes out there. And as a starting point for us, we're very familiar with the implementation of this. And so this is the direction that we went. So we rigged up the Bayesian hyperparameter optimization. And each time the model is run, it's going to use the parameters that outputs from this particular routine. And so this runs through stuff like learning rate, column subsampling, row subsampling. So as the gradient boosted trees are continuing to build further and further. There's a lot of like column sampling and row sampling taking place. And this is a good method for tuning those models. And then, like I said, we just basically rigged up the XGBoost model to then take the Bayesian hyperparameters that were recommended to us. And that was really kind of the final piece of the model pipeline. So we had the ingestion piece, the snowflake piece, we had the data engineering, the feature engineering, we have the model implemented at this point. And then we can just run it. And so now that everything was set up, you know, it was probably like 11:30 or midnight at this point, the day before the submission. And so we get the test or the test data that we can run the models on. And so we ran those through the models. And so here's a couple of examples. Obviously, I cherry-picked the ones that were going to be the best. So we had a couple of good sets here. This 134067. This was the 6 times input output one. Did pretty well there. We had about 92% accuracy on this one. And then this 266510 was the slopes one I showed you guys earlier as well. Did okay with that one. But interestingly, you know, where the model really does break down, and I think an area where we need to continue developing this is it's really hard to differentiate between partially correct and fully correct. And so I think that there's some additional work to be done on being able to like maybe take some steps here. If I know something's not wrong, like go ahead and set it aside. That's not wrong, and then do some additional routines on the remaining data. And then there's also some class imbalance issues that we're dealing with as well. Some questions students just really didn't do very well on, you know, as a collective unit. So, and then finally, in the spirit of trying to keep this as interpretable as we can, you know, we know what the likelihood estimates are that they're getting the constructed responses correct. We can look at the vocabulary. We know what terms are being used in the NLP process. We know the question-specific features that are being used. We're using an XGBoost model. It's a gradient boosted tree. There's not a lot of like neural network stuff going on. So finally, we used Shapley library. A lot of you guys are familiar with this. I've seen it in a couple of presentations today. To better understand the importance of specific features in the system itself. And so these are the same 2 questions, 6 times input equals output, and the slopes question. Interestingly, you can see on this one, it's not actually the constructed response that is the most important feature here, but that key number. Question-specific feature, and as you guys recall, that was 6. If you have 6 in the constructed response, then you get this. If not, you don't. So that was the most important there. And then in this slopes one, the NLP constructed response portion was the most impactful here. Interestingly, we do see also. You hear some part A eliminations, like what they eliminated, but you also do see some of the interaction terms are showing up in the model, the ESL and race interaction terms as well. So, so this was a really interesting and fun project. I think that there's a lot of work to do if we're going to take something like this seriously and really try to implement this on a large scale. But what I feel good about is being able to have gotten to this particular point, knowing the limitations, but still knowing how transparent it is. And now we can like start to dial up some of the sophistication, but trying to preserve that interpretability that is what has been developed today as kind of like the base model for further iterations.
I had a question. You talked about this a little bit with the difference between fully correct and partial correct. And I don't know too terribly much about machine learning at this point, but how do you account for questions where the correct answer and an incorrect or almost correct answer could be written with almost all the same words, but the key concept could still be explained incorrectly?
Yeah, that's a really good point. So the title of the paper that we submitted for this was, I can't remember off the top of my head, but it was a probabilistic approach to this. And basically, we are making some assumptions based on the content of the constructed response. And, I think that is an area where if we were to employ maybe some of the LSTM framework, where it takes sequential context into play, that I think could probably replace that.
Yeah. So to make sure I'm understanding this, these tests were graded by actual teachers, correct?
Yeah, they were graded by actual teachers. Yeah.
So I'm guessing since it was 2 different years, 2 different grades, you got different sets of teachers.
Yeah, that's right.
How did you control for teacher biases?
Yeah, no, that's a good point. So we had no visibility into the graders themselves. So what's interesting is in the human to human QWK being close to 1, I think it ensures or maybe makes people feel comfortable that there's not a ton of bias across the human raters. But if you just think about it, I mean, people get tired, if I'm grading tons of papers, I get tired. Or if you're professors even hold biases against kids. They might like somebody. And so, yeah, that does exist. That does exist.
So that,
I know, I told him to cut his hair. Yeah.
so that stat right there is what you're basically trying to sit there and get as close to 1, and if you're.
Yeah, so if you could put this machine up against a random set of humans, we would want it to be as close.
You talk a lot about interpretability. I'm curious actually your thoughts on if you think going forward, people are going to try to make more interpretable models more accurate, or whether they're going to focus more on trying to make what are now uninterpretable more interpretable.
Yeah, I mean,
Because I've got my thoughts, but I'm curious. You focus so heavily on in this. I'm curious what you're.
that's a great question. I think it depends on where you're coming from and the application of it. I personally believe with this particular application, it needed to be as transparent as you could possibly make it, and having a solution that was not, wasn't going to fly. I mean, for one, it wouldn't have won them. Although I guess some neural networks did win it, so maybe I should have considered that. But if you imagine a world in which something like this is being administered wide scale across the United States and nobody knows what's going on with it, I mean that's not gonna work. I personally approach modeling, even outside of this, just my own professional career, from a story first perspective. I don't really go in and fit a model and then build the story around the model. I think about what logically makes sense here, using my domain specific knowledge, and then construct features to test whether I can actually tease that relationship out. So I tend to start from a place of interpretability, but I think as things become more complex, sophisticated, and these applications are being used for like autonomous driving and stuff like that, I mean it's probably more of an accuracy thing. Foremost, I would imagine.
A question about your own paper?
No, I'm good. So, thank you, Wes. One of the things I wanted to bring you all's attention to is that the NAEP is actually, it's a national report card. It started administered in 1970. So all the 9-year-olds, 13-year-olds, 17-year-olds, they all take this test. This is historical data. Anytime you've heard about the news report talking about the test score has declined or there's learning loss, anything like that is coming from this. It's coming from this NAEP data. This is the first time, historically, first time ever they have allowed industry people and academia people to get together to work on the practical challenge like this. This has huge implication for predicting science test score results, because math is actually okay. You can do some of this, through machines a little bit easier, but science, think about the science. So anyway, there's just a ton of application of this, and this is the first time ever, right, they have released a backup, so. Just provide a little bit of context to what Quest